After studying this chapter, you will be able to explain Rutherford alpha particle scattering experiment, understand Rutherford's and Bohr's model of atom, describe atomic spectrum of hydrogen, understand the concept of isotopes, isobars and isotones, explain radioactive processes, define mass and energy according to Einstein, describe nuclear binding energy and mass defect, explain nuclear fission and nuclear fusion. Hello students, let us have a look at our 9th chapter, that is atoms and nuclei. We will first try to understand what are atoms and nuclei. Each atom has a nucleus consisting of 1 or more protons and 0 or more neutrons. Each proton carries 1 unit of positive electrical charge. In contrast, neutrons are electrically neutral. The nucleus carries exactly same units of positive electrical charge as proton. The number of protons are called atomic number. Rutherford alpha particle scattering experiment. Alpha and beta radiations were identified by Rutherford in 1899. Alpha, beta and gamma radiations can be distinguished by their penetrating powers. Rutherford and his team were developing the cloud chamber, a device for showing the tracks of radiation. Mostly alpha particle tracks show hundreds of tiny deflections. Occasionally major deviations can be seen. Rutherford guessed that the many small deflections were caused by collisions with the very light electrons, while the very rare big deflections arose from collisions with something representing a more concentrated part of the atom. If alpha radiation was expected to pass right through the gold foil, the alpha scattering experiment was designed to allow the detector to be moved around through an angle of greater than 90 degrees. Rutherford's model of atom. British physicist Ernest Rutherford has created a planetary model of atom exploring a dispersion of A particles transisting through a thin metal foil. According to this model, an atom looks like a tiny planetary system in which the forces of an electrical attraction operate. The center of an atom is a positively charged kern. Almost all mass of an atom is focused there. Negatively charged electrons rotate around the kern. An atom of hydrogen has a simpler structure. Positively charged kern of an atom of hydrogen was called a proton. The only electron rotates around it. It was determined later that every atom's kern consists of protons and neutrons. The neutron's mass is almost equal to protons but has not electric charge. The mass of an electron is about 1 by 1840 of a proton's mass and does not influence an atomic weight of substance. According to the Rutherford's experimental results, the radius of a trajectory of an electron in a hydrogen atom is 1.0 into 10 to the power minus 10 m. The diameter of an atom of hydrogen is equal to 2.6 into 10 to the power minus 15 m. Bohr model of the atom. The Bohr model is a planetary model in which the negatively charged electrons orbit a small positively charged nucleus. Electrons orbit the nucleus in orbits that have a set size and energy. The energy of the orbit is related to its size. The lowest energy is found in the smallest orbit. Radiation is absorbed or emitted when an electron moves from one orbit to another. Energy levels of electrons. An atom consists of electrons orbiting around a nucleus. Electrons can jump from one energy level to another, but they can never have orbits with energies other than the allowed energy levels. The electron can gain the energy it needs by absorbing light. If the electron jumps from the second energy level down to the first energy level, it must give off some energy by emitting light. The energy that a photon carries depends on its wavelength. Since the photons absorbed or emitted by electrons jumping between the n is equal to 1 and n is equal to 2 energy levels must have exactly 10.2 eV of energy, the light absorbed or emitted must have a definite wavelength. This wavelength can be found from the equation atomic spectrum of hydrogen. Each element gives a characteristic line spectrum, the lines arising from electron transitions within the atom. With one electron and one proton, hydrogen is the simplest element and gives the simplest line spectrum. There are actually three series of lines in the hydrogen spectrum. One in the infrared region, one in the visible region, and one in the ultraviolet region. The ultraviolet series involves transitions to the first energy level, n is equal to 1 of the hydrogen atom. The visible series involves transitions to the second energy level, n is equal to 2, and the infrared series involves transitions to the third energy level. The energy of electromagnetic radiation is indirectly related to wavelength, meaning that the longer the wavelength, the lower the energy. Therefore, given the four visible lines above, the red line at 656 nm is the longest wavelength and must correspond to the lowest energy transition 3 to 2. Similarly, the blue-green line at 486 nm corresponds to the next lowest energy transition 4 to 2 and so on. Size of nucleus. A nucleus is made up of positively charged protons and neutral, no-charge neutrons, which are collectively called nucleons. The nucleons are made up of quarks and have a radius of about 0.8 fm. There is a very strong and very short-range force that pulls nucleons towards each other and an even stronger repulsive force that keeps them from overlapping each other. The result is that a nucleus looks like a closely packed set of spheres that are almost touching one another. Lithium nucleus has 3 protons, which give the nucleus a charge of positive 3, identifying it as the element lithium, and 4 neutrons, giving it a total mass number of 7. Natural lithium is made up of 2 isotopes, lithium -7, 92.5%, and lithium -6, 7.5%. Lithium -6 has 3 protons, as it must if it is to be the element lithium, but only 3 neutrons, so it has a mass number of 6. Isotopes, isobars and isotones. These are the elements having some atomic number but different mass number. They have the same atomic number because the number of protons inside their nuclei remains the same. The difference in their mass number is due to the difference in their number of neutrons. 1H1, 1H2, 1H3 are all isotopes of hydrogen. They all have their atomic number to be unity, but the number of neutrons is 0, 1, 2 and Z respectively. Isobars are elements which are chemically different but physically same. So isobars are atoms of different elements having the same atomic mass but different atomic number. Isotones are elements having the same number of neutrons. Examples of isotones are chlorine 37 and potassium 39. Both have 20 neutrons in their nuclei. Radioactive processes. In radioactive processes, particles or electromagnetic radiation are emitted from the nucleus. The most common forms of radiation emitted have been traditionally classified as alpha, beta and gamma radiation. Nuclear radiation occurs in other forms, including the emission. Alpha particles, beta particles, gamma rays. Alpha particles are made of 2 protons and 2 neutrons. This means that their charge is +2. Also, an alpha particle is the nucleus of a helium atom, which is the most stable nucleus. An alpha particle has the mass of 4 atomic mass units, which is more than 7,000 times the mass of a beta particle. Beta particles are made up of only one electron. This means that their charge is -1. They have a much greater penetration range than an alpha particle, but it is still far lower when compared to gamma rays. A beta particle has a mass of 1/2000th of a proton, making its mass about 0.002 atomic mass units. Gamma rays are the strongest of these 3 types of radiation. Gamma rays are electromagnetic rays and thus have no charge or mass. When an atom emits an alpha or beta particle, it is possible that the atom may have too much excess energy. In this circumstance, the atom can emit a high frequency wave called a gamma ray. Unlike alpha or beta particles, gamma rays do not pull electrons off of nearby atoms and do not react very much with the surrounding atoms. The law of radioactive decay. The law of radioactive decay predicts how the number of the not decayed nuclei of a given radioactive substance decreases in the course of time. The red circles of this simulation symbolize 1000 atomic nuclei of a radioactive substance whose half-life period T amounts to 20 seconds. The diagram in the lower part of the applet represents the fraction of the not yet decayed nuclei, N by NO at a given time T predicted by the law. Mass and energy. In the special theory of relativity, Einstein demonstrated that neither mass nor energy was conserved separately, but that they could be traded one for the other and only the total mass energy was conserved. The relationship between the mass and the energy is contained in what is probably the most famous equation in science, E is equal to mc square, where m is the mass, c is the speed of light, and E is the energy equivalent of the mass. Nuclear binding energy and mass defect. Nuclear binding energy is the energy required to split a nucleus of an atom into its component parts. The component parts are neutrons and protons, which are collectively called nucleons. The binding energy of nuclei is, as always, a positive number, since all nuclei require net energy to separate them into individual protons and neutrons. Nuclear binding energy is also used to determine whether fission or fusion will be a favorable process. Mass defect is defined as the difference between the mass of a nucleus and the mass of the masses of the nucleons of which it is composed. The mass defect is determined by calculating 3 quantities. These are the actual mass of the nucleus, the composition of the nucleus, number of protons and of neutrons, and the summed masses of that many individual protons and neutrons. Nuclear fusion. Nuclear fission is a nuclear reaction that splits the nucleus of an atom into smaller subatomic particles. It often produces free neutrons and photons. Fission of heavy elements can release large amounts of energy as electromagnetic and kinetic energy. For fission to produce energy, the total binding energy of the resulting element has to be lower than that of the original element. For potential nuclear energy sources for the Earth, the deuterium-tritium fusion reaction contained by some kind of magnetic confinement seems the most likely path. If light nuclei are forced together, they will fuse with a yield of energy because the mass of the combination will be less than the sum of the masses of the individual nuclei. If the combined nuclear mass is less than that of iron at the peak of the binding energy curve, then the nuclear particles will be more tightly bound than they were in the lighter nuclei, and that decrease in mass comes off in the form of energy.